So let's look at the function y equal to, what do I got? I don't know. Sine to the fourth of x over x cubed times the square root of x plus 1. I want to take the derivative of that, and I'm going to use logarithmic differentiation, even though you don't have to. You could totally do this problem using just the product and the product and the quotient and the chain rule. And that's an x cubed, by the way. But you can also use this process called logarithmic differentiation. The whole point is to make things easier. I think it just froze for a second there. Anyway, so I'm going to take the natural log of both sides, and that's always the first step when you're using logarithmic differentiation, is to take the natural log of both sides. So the natural log of y equals the natural log of all this. Now the point is that there are logarithmic rules we can apply to make this expression nicer, right? That looks terrible. So I'm going to use the rules of logarithms to make this into a bunch of simpler logarithms. So I'm going to simplify. Meaning, the left-hand side is going to stay the same. And the right-hand side, well, the natural log of something divided by something else is the natural log of the first thing. So it's the natural log of sine to the fourth of x minus the natural log of x cubed times x plus 1 to the 1/2. And then we can break this up even more. We can write this as, I'm going to write this as the natural log of sine of x to the fourth. Now be careful here. This is going to be minus the natural log of x cubed minus the natural log of x plus 1 to the 1/2. Really, here's what's happening. Really, it's a minus the natural log of x cubed plus the natural log of x plus 1 to the 1/2. Right? I'm using the product rule for logs. It says the natural log of something times something else is the natural log of the first thing plus the natural log of the second thing. Then I'm also distributing the minus sign to each of those. And then finally, before we do any differentiating here, we're still just simplifying. We're going to bring down the powers. So that natural log of y is equal to the 4 times the natural log of sine of x minus 3 times the natural log of x minus 1/2, right? Because it's a minus the natural log of x plus 1. So that's kind of the beginning of the logarithmic differentiation process. Is take the natural log of both sides and then simplify the side that's really the side that's like not the y side, the other side that's complicated. And then finally, after we've done as much simplifying as possible, we're going to differentiate both sides. I guess I'm going to do that on the other side of the board because I'm running out of room. So I've got natural log of y equals 4, natural log of sine, minus 3, natural log of x. So natural log of y equals 4, natural log of sine, minus 3, that's a 3, believe it or not, natural log of x, minus 1/2 natural log of x plus 1. And now we're going to differentiate both sides. And we're going to differentiate the left side. So let me ask you guys, what's the derivative of the natural log of y?
1 over y?
That's most of it. It is definitely 1 over y times something.
dy dx.
Exactly, dy dx or y prime, either way. All right, dy dx. Yeah, right, we're using implicit differentiation here. Say, oh yeah, the derivative of natural log of a function of x is 1 over the thing times the derivative of that function of x. On the right-hand side, we don't have to do that. We're just going to take the derivative as normal. Well, I mean, we're still going to use the chain rule, though, right? That's what we did here. We use the chain rule, 1 over the stuff times the derivative of the stuff. Same idea here. Constant multiples hang out. So I get 4 times the derivative of the natural log of sine is 1 over sine times what?
Cosine.
Thank you. And then minus 3 times, okay, the derivative of the natural log of x is just 1 over x. Minus 1/2 times the derivative of the natural log of x plus 1 is 1 over x plus 1 times 1, right? Because the derivative of x plus 1 is just 1. And then finally, you would multiply both sides by y. So dy dx. And when I do this, I also simplify it a little bit. So I'm going to say this is going to be y times all of this. This part here I'm going to simplify because cosine divided by sine is cotangent. So like this is 4 cotangent of x minus 3 over x minus 1 over 2 times x plus 1. Now it's not the last step because our original expression was a function of x. Our final answer derivative should be also a function of just x without any y's in it. So our last step is to replace y with the function it's equal to, which is sine to the fourth x over x cubed times square root of x plus 1. So we're going to rewrite this as dy dx equals sine to the fourth x over x cubed x plus 1 times all this. Now, for this particular problem, I personally probably wouldn't choose to use logarithmic differentiation. I would probably do it the other way. So let me show you that because I think it is worth doing this the other way to kind of talk about that as well. But this is, so again, for those of you that just joined us, this is the process of logarithmic differentiation, even when it's not absolutely necessary. You take the natural log of both sides, you simplify the side that's super complicated as much as possible. So I've seen a lot of people do this, but stop like here or stop here before they brought down the powers. You really want to simplify these logs as much as you can because then their derivatives are way easier. Taking the derivative of 4 natural log of sine is much simpler than taking the derivative of the natural log of sine to the fourth. So do really simplify these logs as much as possible. And then you would differentiate both sides using implicit on the left and then solve for dy dx by multiplying both sides by y and replacing it. But let me show you. We could also have done this one the regular way. Meaning we could just take the derivative here. We can say, all right, I'm going to use the quotient and the product and the chain rule. So I'm going to rewrite this just for a second as sine of x to the fourth over x cubed times x plus 1 to the 1/2. Taking the derivative, dy dx. So I'm going to use the quotient rule because the quotient is kind of the, I was plugging in x, the fraction part is kind of the last part I would do. So it's going to be the bottom, x cubed times x plus 1 to the 1/2 times the derivative of the top. Okay, the derivative of some stuff to the fourth power is 4 times my stuff to the third power times the derivative of that stuff, which is cosine of x, minus, now we switch it. So we did bottom times derivative of the top. Now we're doing top times derivative of the bottom. Notice that I didn't write parentheses around all this because everything is just multiplied together. I don't have things added together, so I didn't write parentheses. You could write parentheses, that would be okay. So bottom derivative of the top minus the top times the derivative of the bottom. For the derivative of the bottom, we have to use the product rule. So it's going to be the derivative of x cubed, which is 3x squared, times that left alone. And then flip it plus x cubed times the derivative of x plus 1 to the 1/2, which is 1/2 times my stuff to the negative 1/2 times the derivative of my stuff. But fortunately here, the derivative of that stuff is just 1 over the denominator squared. Which you could simplify this denominator as x to the 6th times x plus 1, right? Because of the squared. So I don't know if this is better or worse. This feels worse, I gotta say. Doing it the other, which I know, so we simplified, right? We took the natural log of both sides and wrote this way. I feel like this kind of feels better, I'm not gonna lie. So logarithmic differentiation, even when you don't absolutely have to use it, is still sometimes really nice. If you got a terrible rational expression with lots of factors multiplied together, that's a good time to use logarithmic differentiation. Honestly though, where this particular kind of thing usually comes up is people will just kind of ask you to say, hey, I want you to take the derivative of f of x equal to the natural log of something terrible, like x to the fourth times sine squared of x over x plus 1 cubed times cosine of x. right? Here you don't have to use the process of logarithmic differentiation because you already have a natural log here. Here the idea is just to simplify this using the rules of logarithms and then differentiating both sides. So here, I'm going to do this one real quick. You would write this. So watch me simplify this. I see 1, 2, 3, 4 factors. The factors in the top are positive when we break this apart into 4 pieces, or 4 logarithms. The factors in the bottom end up having minus signs because you're dividing by them and you get a minus sign. And then the powers, the 4, the 2, the 3, and the 1 are going to come down. So here's how this simplifies in one fast step. It's 4 natural log of x plus 2 natural log of sine of x minus 3 natural log of x plus 1 minus natural log of cosine of x. You know, it's kind of a lot at once. Normally, I would probably do this in 2 steps. My step before this would have been the natural log of x to the 4th plus the natural log of sine squared x minus the natural log of x plus 1 cubed minus the natural log of cosine of x. And I will point out one more time, the reason it's a minus and a minus here is because really it would have been a minus that plus that. We distribute the minus sign. So you'll see this often. We're like, oh, take the derivative of this. And the whole point is not to do it terribly, right? Don't do 1 over all this stuff times the derivative of all this stuff. That's awful. Simplify this like this so that then you can say, oh, then f prime of x is just the derivative of all these nice simple logarithms. It's 4 times 1 over x plus 2 times 1 over sine of x times the derivative of sine of x minus 3 times 1 over x plus 1 minus 1 over cosine of x times the derivative of cosine of x, which is negative sine of x. Right, that's how you're meant to do that kind of problem. Okay, that said, so if you've got your function equal to a logarithm of some garbage, you just take the derivative by simplifying first. If you've got your function just equal to some terrible garbage, you can do the process of taking the log of both sides and simplifying the right-hand side and then differentiating, but then you have to do the whole process where you then multiply back by y. Okay, but then there are some functions where you kind of have to use logarithmic differentiation. And I say have to, technically you probably never actually have to use logarithmic differentiation, but it's really kind of the nicest way. So for example, if I want to find the derivative of, say, I don't know, let's do something like, so, and these are problems, this is problem like 37, 38 in your book, etc. Let's say I want to take the derivative of something like x cubed plus x to the sine of x power. And so I know, and you will know, that when you have a variable in your base and in your exponent, that is the time to use logarithmic differentiation. So, and the problem with that is you kind of have to know one thing. You have to know, oh, I have to rewrite this. I have to write it as, let's do it this way, y equal to the function you're trying to differentiate. And the reason you have to rewrite it, oh, sorry, it's sine of x, not cosine of x. The reason you have to rewrite it is because you have to be able to take the natural log of both sides. And if you don't have one side equal to another side, you can't do that. So whenever you say, oh, I think I need to use logarithmic differentiation, you should also say to yourself, I have to write it as y equal to. Lots of times they'll just give it to you that way as kind of a clue that you should be using logarithmic differentiation, but sometimes they won't if they're mean. So then we're going to take the natural log of both sides. Take natural log of both sides. So we're going to get the natural log of y equal to the natural log of all of that. X cubed plus x to the sine of x. Now, why would we do this? The reason we would do this is because taking the natural log of something to a power allows us to bring down that power in front of the natural log. So I can rewrite this as the natural log of y equals sine of x times the natural log of x cubed plus x. And now we are able to differentiate the right-hand side. Right? We didn't know how to differentiate this to this power. If there isn't, I mean, there's kind of a weird funky rule for something to a power where both the base and the something to the power have exponents, but it's or sorry, have variables, but it's really not a rule that you want to memorize. Instead, we're going to do it this way, and then we're going to say, oh, I can take the derivative of this right-hand side using the product and the chain rule. So let's differentiate both sides. Differentiate. The derivative of the natural log of y is always going to be 1 over y times y prime if we're thinking of y as a function of x. And y is definitely a function of x. So the derivative of the natural log of y is 1 over my y times my y prime, or 1 over my stuff times the derivative of my stuff. And then we're going to differentiate the right-hand side using the product rule. So the derivative of sine of x is cosine of x times, leave the other piece alone, plus leave the sine of x alone, multiply by the derivative of the natural log of x cubed plus x, which is 1 over the stuff times the derivative of that stuff, which is 3x squared plus 1. Okay, lastly, we have to solve for y prime. Now, I personally think it's perfectly good to bring over the y and replace it with what it's equal to, but some people like to do it in 2 steps. So I'll do it in 2 steps. So the first step, multiply both sides by y. So on the left, the y cancels. In fact, we can even, right? So we could write in a y here and a y here. So on this side, we cancel the y's. So we get y prime equal to, now we could write y times all that stuff, and maybe I would, but really I want to replace y with what y is equal to, so that my answer, my derivative, is still just in terms of x. So I'm going to have x cubed plus x to the sine of x times all of this stuff, which I might simplify just a little bit. There's really not a lot of simplifying to do, but there's one thing I can do really. It's cosine of x times the natural log of x cubed plus x, plus I would probably write this as sine of x times this over that. 3x squared plus 1 over x cubed. And that would be our final answer. Are there questions about this?
Yeah, I have a question. Like for the when you do the simplifying and you're getting rid of like for the the second to the last one and you put it like 1 over whatever the stuff is, like why are you? Can you clarify why you do that again?
This right here?
Yeah.
So when I took the derivative or when I went to the next step?
When you got the derivative, like when you got that fraction.
Sure. So when you take, so what's the derivative of the natural log of x?
Oh, okay. It would just be like the. Well, like, are you looking at it in terms of just like having it as like 10, like when you do the?
That's a different question. So I'm very, very, very straightforward. What's the derivative of just the natural log of x?
Would it be like 1 over the x?
Right, exactly, 1 over x. And so
Okay.
all I'm doing on the other side is saying, oh, well, I'm using the chain rule version, saying the derivative of the natural log of some stuff. 1 over the stuff, but then what do I have to multiply by? The derivative of the stuff.
Okay.
So here, when I'm taking the derivative of the natural log of some stuff, I'm getting 1 over the stuff times the derivative of that stuff.
And then, since for the other side next to the cosine, since that one you didn't add the ln yet, you don't do that process.
Sorry, say that one more time. So over here,
On the like right there where you add the ln, you don't do it over
I'm not adding.
I mean, multiplying it. I meant like you were adding it to the situation because before were just the sine x, like you didn't have that.
Sure.
But
So,
now you,
so what I'm doing is I'm using the product rule, right? Here, that's the derivative of sine times not the derivative of the natural log.
mm-hmm.
So this is my f and this is my g. This is my f prime. This is just g. This is my f. This is my g.
Oh, okay. Okay, that makes sense.
Make sense?
Yeah.
Yeah. So, and for these ones where it's again, both where when you have a base and a power that both have a variable, which will mean you'll need to use this process of logarithmic differentiation, you'll always end up getting to a point where you're going to have to use the product rule. Because you'll have taken the natural log of this side, you'll have brought down the power, and both the thing that you brought down and the natural log of your stuff, both of those will be functions of x multiplied together, which means we have to use the product rule. Let's do another example. But again, this is always the process. It's always the same, like 4 steps. I could make it, that's an interesting idea. So yeah, it seems unnecessarily complicated. Let's see, I want to find the derivative of, so I want to find dy dx for y equal to, what kind of heinous thing do I want to come up with here? Your book has an, that's sure. Let's do secant of x to the 1 over x power. That seems interesting. Same first step. Take the natural log of both sides. So natural log of y equals the natural log of secant of x to the 1 over x. And then we're going to bring down that power of 1 over x. So I'm going to rewrite this as the natural log of y equal to 1 over x times the natural log of secant of x. Now, we do have a choice here. We could either think of this as 1 over x times the natural log of secant of x and use the product rule. Or if we wanted to, we could think of it as the natural log of secant of x divided by x and use the quotient rule. It's really the same work either way, or it's very similar work either way. I'll show both. So doing it this way, I'm going to take the derivative of the left, which is 1 over y prime, equals the derivative of 1 over x. I would really rather think of that as x to the minus 1. So this is x to the minus 1, and its derivative is minus 1 times x to the minus 2, or minus x to the minus 2, times this left alone. Right? I'm using the product rule, so it's the derivative of that times that, plus, now I flip it. I leave this one alone, it's x to the negative 1, times the derivative of the natural log of secant, which is, I'm going to run out of room here, so maybe I'll do this one on the other side. So the derivative of the natural log of secant is 1 over my stuff times the derivative of my stuff, and the derivative of secant of x is secant x times tangent x. Okay, so then we multiply both sides by y, and we simplify this. I also want to I'm going to remind everybody again, right? I'm just doing the product rule here, right? If this is my function f, this is my function g, here's f prime, here's g, here's f, here's g prime. Okay, so then if we simplify, so we're going to get y prime equal to y times all this. And I don't really know what simplifying we should do, to be honest. I would maybe leave this like this. You could also write this as the negative natural log of secant of x over x to the positive second. And then you could rewrite this as plus 1 over x times the secant here cancels the secant there, so you just have a tangent. Finally, we always have to do this. We replace the y here with what y is actually equal to. So that we actually get y prime equal to that secant of x to the 1 over x power times all of this. Negative natural log of secant of x over x squared. And I would probably write this as plus tangent of x over x. So that's how that one works out. Or we could do it with the quotient rule. I don't really think we should, though, unless someone really, really wants me to. Okay. Hearing no requests for that. This is the process, right? It's kind of the same process every time for logarithmic differentiation. So I think that's enough. We could do one more if you guys really want, but it's kind of the same thing every time. So let's go ahead and look a little more at exponential growth and decay, as well as Newton's law of cooling. Let me grab my examples here before I get too carried away. Also, while I have a second, let me screenshot the attendance because there's like a million of you. I would like to make sure everybody gets counted. Okay. Do like 3 pictures because there's so many of you guys. Maybe just 2. Probably don't want to. There we go. Great. Now hopefully no one else shows up, so I don't have to remember that. Okay. Let's look at. Where'd you go? So last time we had talked about exponential growth and decay just a little bit, and I really just want to remind you, it's kind of the same stuff. Like, ooh, gross. This black dust is disgusting, especially when it gets under your nails. Black bread, whatever color it is, it's all gross. So exponential growth and decay. Exponential growth and decay. You're always thinking of, I'm going to have this kind of setup where you've got y equals c e to the kt. And sometimes books use different notations depending on what they're talking about. Sometimes they'll write like p equals p naught e to the rt, or m equals m naught e to the kt. You shouldn't concern yourself really with what letters they're using there. It doesn't really matter. The reasons people might use these different ones, like people kind of use these letters if you're talking about population growth, P for population, and P naught is the initial population. And sometimes people use this M and M naught for if you're talking about the mass of a radioactive material, M for mass. But you can use whatever letters you want. So let's say we have this sort of situation. We have, let's say radioactive, I'm just going to make something up, radioactive parmentonium, my favorite element, parmentonium, yeah, I just discovered it. It's got a very convenient half-life, not some weird number like 5,100 and whatever, has a half-life of, let's say, 200 years. And we have 70% of our original sample. How much, or I should say, yeah, when will only 10% of the original sample remain? Okay, so one of the points of this problem is to point out kind of a thing that's true. No one told us how much stuff we have. And especially if you're just being told percentages about like how much you have at a certain time, you can kind of pick whatever number you want. Now I will say, sometimes that's not true if they're asking you like to use the information to figure out how much you started with. Usually then they're actually giving you a value at some later time. Here they're just saying we have percents. And so what we can do is you can say, I'm going to say I want to start with a very convenient number if I'm dealing with percents. I'm going to say at time 0, I have 100. I don't even care what units really. I'm going to say 100 grams. Why not? And then I'm going to use this information to, you know what I forgot to do? I was like, I knew I, yeah. So, no, I guess I've given enough information here. So, we need to figure this out. But when I say we need to figure this out, what I mean is we need to figure out what the C and the K are. So we have the model, so that then we can figure out when there's only going to be 10% left. So we know that at some time later, we don't know when, that's kind of our starting point. There's going to be 70%, which is just 70. That's why I used 100. We know that at some other time later, there's going to be 10%, which is 10 grams. We also know that after 200 years, there are exactly half as many grams as we started with. Okay, so let's use this piece of data to figure out what our K is. Why am I not talking about C? Well, because we already know what C is. C is the initial amount you're starting with. So I'm going to say Y equals 100 e to the KT. And then I'm going to plug in, sure, yeah. I'm going to plug in 200 for Y. I'm sorry, 200 for T and 50 for Y. So I'm going to have 50 equal to 100 e to the K times 200. I kind of want to erase this, but I feel like that would not be a good idea, so let's just not erase it for now. I'm going to have to use the other side of the board. So solving this equation, I'm going to divide both sides by 100. 50 over 100 is 1/2. And then 1/2 is equal to e to the K times 200. Take the natural log of both sides. The natural log of 1/2 equals, the natural log of e to the thing is just the thing. So the natural log of e to the K times 200 is just K times 200. And finally, dividing by 200 for K, I should say to solve for K, we get K is the natural log of 1/2 over 200. So our model here is Y equal to C to the KT, which is Y equal to 100 e to the K, which is this first number here, T. So it's Y equal to 100 e to the natural log of 1/2 over 200 T. Okay, so now we have the model. Now we're trying to figure out what's what. And the problem is, the way we set this up, or the problem is the way I phrase this question makes it challenging, right? We started off with 70%. So we kind of have to figure out the time we're at here and then figure out how much time elapses to get to here, which is kind of annoying. But yeah, I can erase this now. So that's what we're going to do. We're going to figure out what time it is at 70%. And that's kind of our initial time, and figure out how much time further. So really, we're just trying to find these two times and then find the difference between them. So to find this time, we're going to plug in Y equal to 70. So we're going to say, okay, Y equal to 70. So 70 equals 100 e to the natural log of 1/2 over 200 t. And we're going to solve for t. Divide both sides by 100. Not surprisingly, we get 0.7. When you're dealing with percentages, once you've divided both sides by this coefficient, you're almost always going to get the number over here that's your percentage as a decimal, right? Half-life was 200 years. Once we divided both sides by 50, we got 0.5. Here, we're dividing both sides by 100. Sorry, before we should divide both sides by 100, not by 50. Anyway, we get 0.7 equal to e to the natural log of 1/2 over 200 t. Sorry, I know things are getting kind of crammed in there. Take the natural log of both sides. Natural log of 0.7 equals the natural log of e to a power is just the power. So it's natural log of 1/2 over 200 times t. Solve for t by multiplying by 200 divided by natural log of 1/2. So time here is 200 natural log of 0.7 divided by natural log of 1/2, which is approximately, let's figure out what that is approximately. It's going to be, let's see, natural log of 0.7 divided by natural log of 0.5 times 200. It's going to be about 102 years. Approximately 102.9 years. So that's kind of when we're starting, right? We're starting at year 102.9. And then we're going to figure out how long it takes to get the time. Now, yeah. So sure. So then we're going to say, all right, how long does it take to get to just having 10 grams? Well, 10 equals 100 e to the natural log of 1/2 over 200 t. We could go through the same 3 steps, but I would like to think that you guys can see that it's going to be exactly the same result, except instead of having 0.7 over here, when I divide by 100, I'm going to have 0.1. So my answer should be, if I do those same 3 steps, time equal to 200 times the natural log of 0.1 over the natural log of 1/2. I can explain that. I'm happy to, right? We divide both sides by 100, we get 0.1 equal to e to the natural log of 1/2 over 200 times t. Take the natural log of both sides. Natural log of e to the thing is just the thing. And then finally we solve for t by multiplying by 200 and dividing by natural log of 1/2. But I think that if you can see that these are essentially the same processes and you're just having a different number in one spot, you don't have to show all that work. So simplifying that, we get, let's see here, 200 times natural log of 0.1 divided by natural log of 0.5. You get about 664.4. So from here to here, it was about, so elapsed time from starting at 70% and ending at 10% is going to be this minus this. So approximately 560, 61.5 years. Okay. So when you're dealing with exponential growth and decay problems, it's really kind of just, you're going to have some times and some amounts. You're going to use those to find the C and the K in the model. And then you're going to, after you've done that, substitute in whatever known times or values you have so that you can solve for what they're asking for. And usually the questions are, what time is it when I have so many grams or so many people or so much stuff? Or, so basically I can tell you a time and ask you how much stuff there is, or I can tell you how much stuff there is and ask you for a time. It's kind of really all the stuff we can ask for. Newton's law of cooling is essentially the same. Let me show you how that works. It's a little bit different, but it really is the same idea in that you do have some sort of exponential decay or growth, depending on if things are getting warmer or if things are getting hotter. I know Newton's law of cooling sounds like we're only talking about things getting colder, but it's really things getting closer to the temperature of the surrounding room. People usually think of it as like you've taken something hot out of the oven, like a turkey is a common example, and it gets cooler because the room is cooler and it's cooling down. But you could also take like a cold soft drink out of the fridge and leave it out on the counter, and it would get warmer because it's going to get closer to the temperature of its surrounding area. So it's really Newton's law of temperatures getting closer to the temperatures of the surrounding environment. That said, here's how it kind of works. So Newton's law of cooling says that the rate of change of temperature, so we're using capital T for temperature and little t for time. The rate of change of temperature is proportional to, so that's what the K is for, it's a constant, some number, proportional to the difference in the temperature of the object. Okay, so capital T is the temperature of the object, like the turkey in the room, and Ts is the temperature of the surrounding environment. And what Newton's law of cooling says is that the rate of change of the temperature of the object, right? So that's temperature of the object. The rate of change of that temperature of the object is proportional to the difference in the temperature of the object and the temperature of the surrounding room. So if there's a big difference in like the temperature of a turkey and the temperature, like say your turkey's say way overcooked, it's like 500 degrees, that'd be terrible, right? It'd be off the turkey. But if it's 500 degrees and the room you're in is 70 degrees, it's going to cool down really fast at the beginning because there's such a big difference in the temperature of the turkey and the temperature of the surrounding room. Whereas if the turkey is a much more normal temperature, like 165 degrees, and the room is still 70 degrees, it's going to not cool down as fast at the beginning or at all because it's a lesser difference. Now, what happens here, the way this kind of is the same as exponential growth and decay, is we can kind of think of this T minus Ts. And again, so I want to point out this T here is variable, right? The temperature of the object is changing. And we're going to assume that this T sub S, the temperature of the surrounding room, is constant, right? Or the environment. We're making the assumption, it's not always exactly true, but we're just going to assume for mathematical purposes that whatever environment you're putting your object into is at a constant temperature. So we can call this thing a Y. And I can say that, okay, well, check this out. If this is Y, so if Y is equal to T minus Ts, where this is a variable and this is a constant, what happens if I differentiate both sides? Well, on the left, I get dy dt. On the right, the derivative of capital T is just the derivative of capital T. And the derivative of this constant is 0. So what we can do is we can actually replace dt dt with dy dt and t minus ts with y. So check this out. It looks exactly like dy dt is proportional to k times y. And this is exactly the equation that the exponential growth / decay equation comes from. So what we end up getting is that y equals c e to the kt. Except it's not y, it's really t minus the surrounding temperature. It's really T minus Ts equals C to the KT. So this is typically how I think of the Newton's law of cooling formula. And I don't know if that's how your book actually gives it to you or not. Let me actually take a real quick look at the book here. They might just give you the actual, because there is a more specific kind of formula. Let me take a look. I don't think they do. Yeah, that's cool. I prefer it that way. All right, so let's look at an example. All right, this is our formula. I'm sorry, I've covered up the chat. I always accidentally cover up the chat because there's just so many things. Okay, no one chatted anything, but this one. Sometimes I accidentally cover up the chat. So, I also say Newton's law of cooling is what you use, or at least what they use in math textbooks. When you've got like a dead body problem, like you've got a body and you found it at some temperature like 90 degrees, and you're like, oh, what time was the person dying at? Well, I used Newton's law of cooling to figure out how much time has passed from when they would have been 98.6 degrees. So in case you're wondering, that's how you solve dead body problems with math. So here is a problem. I think this is problem number 13 from section 3.6. A roast turkey. Someone overcooked it. It is 185 degrees when taken out of the oven and placed into a room that is 75 degrees. So I'll point out, right, this 75-degree room, that's our surrounding temperature. That's our T sub S. And the question is, or I'm sorry, I need to give more information first. If the turkey is 150 degrees after 30 minutes, then what will the temperature be after 45 minutes? And when I say after 45 minutes, I mean after 45 minutes after we took it out, not 45 additional minutes. Okay, so let's set this up. So here's what we know. We know that the temperature of the turkey, which is a variable, sometimes people write this as capital T of little t. The temperature of the turkey at time t is equal to, well, again, it's just this formula, right? Or sorry, it's the temperature minus the surrounding temperature, sorry. Usually people just throw that onto the other side. So I could write it as the temperature minus the surrounding temperature equals C e to the KT. But often what people do is they put this over here and say, okay, so the temperature of my turkey at time t, it's a lot of t's, is equal to the surrounding temperature, which is 75 degrees, plus C e to the KT. And then we're going to use the two pieces of data we have to solve for C and K, just like we would in a regular exponential growth or decay problem. So here's what I know. At time 0, when we take the turkey out, the temperature is 185. And at time 30 minutes later, the temperature is 150. And I want to know the temperature when the time is 45 minutes. So we're going to use these two pieces of data to figure out what C and K are. So let's plug in 0 for time and 185 for temperature and see what we get. So 185 equals 75 plus C, which is, we don't know yet, e to the K times time is 0. So this is e to the 0, which is 1, C times 1. So C is equal to 185. I guess I could have left on the other side. C is equal to 185 minus 75, which is going to give me C equal to 110. And then we're going to plug in the other piece of data to solve for K. So you know what? I know I said people often bring this over here, and I guess we will at the very end. But for these first two steps, it probably actually would have made sense to leave it on the other side. Because in this next step, I'm going to solve for K. And so when I plug in here, it probably makes more sense to write this as the temperature of the turkey minus 75 equals C, which is, oh, sorry, the temperature, I should be plugging in the temperature, which is 150, equals C e to the K times T, which is 30, and I forgot to plug in the C value I just found. The C value is 110. So that's what we're trying to do here. So we're trying to solve for K. So 150 minus 75 is 75. Divide by 110 equals e to the K times 30. Take the natural log of both sides. So natural log of 75 over 110 equals K times 30. And finally divide by 30 to get the K is equal to the natural log of 75 over 110 divided by 30. Okay, we finally figured out the model. So we've got our K, we've got our C. Now we can say that the temperature at time T is equal to 75 plus 110 e to the K, which is natural log of 75 over 110 over 30 times T. So what I want you to remember before I go any further here is that the way you solve these problems is just like solving an exponential growth or decay problem where you have y equal to c e to the kt. The only difference is instead of starting with y equal to c e to the kt, you're starting with your temperature minus your surrounding temperature. So temperature variable minus surrounding temperature constant equal to c e to the kt. It's the only real difference. And then finally, we're going to plug in 45 minutes and get temperature at 45 minutes is equal to 75 plus 110 times e to the natural log of 75 over 110 over 30 times 45. And if I didn't have a calculator, I would just leave it like that. If I did have a calculator, I would give it that's approximately 137 degrees. Oh, I got pat in my hand. I hate when I get pat in my hand. Gross. Are there questions about this? Should we do another example? Should we do a dead body example? Yeah, it's like, we don't care. I bet you care. Yeah, let's do one more example. Because so this next example there is something a little different, but not a lot different. Yeah, I hope the yeah is yes, I do want more. Yeah, okay. So police discover a dead body. This is the problem. I'm actually reading says murder victim, but let's just go with dead body. We don't know they're a murder. That's making some assumptions. If you've ever watched any kind of show, right? We don't know it's murder until they've done the autopsy. Police discover a dead body at 10 p.m. The body temperature is 87 degrees. In a room, in a 70-degree room. 1 hour later, the body temperature is, what have I got here? 86 degrees. When did the murder occur? When did the person die? When did they die? Okay, so same idea. We're going to make a table. Well, I should say first, I'm really first going to write the equation, right? We know our equation is time minus surrounding temperature equals CE to the KT. I'm going to go ahead and plug in for surrounding temperature that value of 70. And I guess they're just leaving the dead body in the room for an hour. Okay, that seems suspect. So let's make our table. So I've got my time and I've got my temperature. So at time 0, which is 10 p.m., right? So you could say 10 p.m., but it's easier if you start kind of the initial time being time 0. So time 0, which is 10 p.m., the body is 87 degrees. And then at time 1, the body is 86 degrees. And we want to know at what time. Oh, what temperature should the body be if I'm trying to figure out the time when they died, meaning the last time they were alive? What's the normal body temperature in Fahrenheit for a human being? Well, at least I should say.
I think it's like 98 point something.
Right, it's 98.6. Which may not actually be true, but it's usually what most textbooks assume. So if someone's asking what's the temperature of a person at when they're alive, 98.6 degrees Fahrenheit, or I think 32 degrees Celsius. No, I'm not sure. How do we convert from Fahrenheit to Celsius? We subtract 32 and we multiply by 5 nines. So 98.6. I'm just curious. Minus 32 times 5 divided by 9. 37 degrees Celsius is the temperature for a human person. Okay, So, same process as before. We're going to plug in our first data point to find the C. We're going to then plug in our second data point to find the K. So plugging in this data point, I'm setting temperature equal to 87 and T equal to 1. Sorry, T equal to 0. So I get C e to the K times 0. So I'm just going to get 17 equal to C. C, this constant here, C, should always be the difference between your object at time 0 and your surrounding temperature. So if your object is hotter, C will be positive. If your object is cooler, C will be negative. So then we're going to go back and we're going to plug in this data point. So we're going to get, all right, temperature 86 minus 70 equals C, which we found to be 17 times e to the K times 1. Okay, 86 minus 70 is 16. 16 equals 17 e to the K. Divide both sides by 17, you get 16 17 equals e to the K. Take the natural log of both sides. And here it was a little easier than before because the coefficient of K was just 1, right? In the previous problem, after we took the natural log of both sides, we also had to divide by that 30 here. Here we don't have to do that because we're plugging in time equal to 1. Okay, so now we're going to have our model. Our model is temperature at time t minus 70 degrees equals C, which is 17, e to the K, which is the natural log of 16 over 17 t. And now we're being asked to figure out when did the person die. So we're going to be plugging in 98.6 degrees for the temperature. So we're going to have, okay, let's do this in red. 98.6 minus 70 equal to 17 e to the natural log of 16 over 17t. And it's just, I mean, the process is the same kind of over and over again, right? You're always just doing the same steps. You're going to subtract these, you're going to get what? 22.6. No, wow. Wow, that was not, I think I was seeing a 6 there for some reason. 98.6 minus 70 should be 28.6. So I'm going to get 28.6 equal to 17 e to the stuff. And I'm going to divide both sides by 17. So I'm going to get 28.7, sorry, 0.6. Jesus, holy moly. 28.6 divided by 17 equal to e to the natural log of 16 17 times t. And then I'm gonna erase stuff up here. And then we're going to take the natural log of both sides. So we have the natural log of 28.6 over 17 equal to e to the natural log of stuff is just the stuff. And finally, solving for t, multiply by 17 divided by 16, so 17 over 16 times the natural log of 28.6 over 17 equals t. Now, what I want you to see about this, did I make a mistake? I did make, man, I'm sorry, I'm making quite a few mistakes here. I made a mistake when I copied from here to here. And I didn't really make a mistake so much as that I took the natural log of both sides, but wasn't careful with the right-hand side. It should be the natural log of 28.6 over 17 equal to the natural log of e to the stuff is just the stuff, which would be the natural log of 16 17 times t. Sorry about that. So then dividing both sides by the natural log of 16 17, so I get the natural log of 28.6 over 17 divided by the natural log of 16 over 17 equal to t. I really want to stress that we can't simplify this really at all. Those 17s definitely don't cancel out. I also want to point out that if you calculate this, it's going to end up being negative. Natural log of 28.6 over 17 is a positive number, because you take the natural log of something that's bigger than 1. But natural log of 16 17 is actually a negative number, taking the natural log of something that's less than 1. So this is going to end up giving you a negative time, and it's going to be approximately negative 8.5. Okay, so then we have to go back and think about what the times mean. Well, time equal to 0 was 10 p.m. So we have to go back in time 8.5 hours before 10 p.m. So time equal to negative 8.5 is going to be 8.5 hours before 10 p.m. or 10 p.m. 10 minus 8.5. So it's going to be 10 minus 8.5, which is 1.5 or 1.5 hours afternoon or 1:30. So yeah, so a lot of these things, right, when you're given like we found something at this time and we want to know what happened this time before it, you have to say to yourself, oh, I'm probably going to get a negative time, which is going to tell me how much time before time equal to 0 I'm actually finding the thing. Okay. So let me see. Let's look at a few examples of. Sorry, I know where I want to look. One sec. I have all of these available. Sure. I said I was going to do related rates, but I feel like I'm right out of time for related rates. So let me do a couple of second derivative problems, and then I have one related rates problem we can do. It's always good to do more related rates problems. So let's say we have something like this. Let's say our function is f of x equal to something gnarly, like, I don't know. I want to make this really gross or just a little bit gross. Just a little bit gross. Let's say it's 6x to the 5th plus 9 to the 10th power. And I want to find the first and the second derivative. And this is actually, it's a good point here. When you're being asked to find more than one derivative of a function, it is often a good idea to simplify as much as possible between taking the first derivative and taking the second derivative. I don't know if there's going to be a lot of simplifying here, but there might be some. So let's find our first derivative. So the derivative of stuff to the 10th power is 10 times my stuff to the 9th power times the derivative of my stuff. What's the derivative of my stuff here?
Is it just 30x to the 4th?
It is just 30x to the 4th. Now, there's not a lot of simplifying to be done here, but I probably would take the small step of rewriting the 10 times 30x to the 4th as 300x to the 4th times 6x to the 5th plus 9 to the 9th. And so when I take the second derivative, I see I'm going to have to do a product rule. And I'm going to think, so there's kind of two ways you can do this. And I mean, they're really the same, but I want to point out, I kind of personally, when I have a constant times something that's easy, I kind of like to think of this as my f, or whatever you want to call it. I guess I shouldn't call this f, right? And this is my g. But some people would prefer to write it as, this is my constant multiple 300 times my f times my g. And we'll do it both ways. Why not? We probably have enough room. So let's take the second derivative here. So f double prime of x. Doing it this way, so what's the derivative? So I'm going to do product rule, right? Derivative of this times that plus the derivative of this times that. So the derivative of 300x to the 4th is 4 times 300 is 1200x to the 3rd times the other part left alone plus, then we switch it, right? We leave this part alone, 300x to the 4th times the derivative of this part, which is going to be, in fact, we already know what the derivative of this part is. Well, essentially, it's going to be times 9 times my stuff to the 8th times the derivative of my stuff. So, and just to make sure everyone can see it, right? It's f prime g plus f g prime. That's certainly a perfectly fine way of doing it. And you could simplify this a little bit, right? You could multiply the 30x to the fourth times the 9 times the 300x to the fourth and get something heinous like 81,000x to the eighth times 6x to the fifth plus 9 to the eighth. I don't think you really need to do that, especially if it's a web work problem. Over here, on the other hand, if I was going to do the derivative this way, the second derivative would be, so that 300 constant is just going to hang out. It's 300 times the derivative of all this. And the derivative of all this is going to be f prime g plus fg prime. So f prime is 4x cubed times g left alone. Sorry, I don't really have enough room here. Oops, that's not what I wanted. Plus, then we switch it. We do the x to the fourth left alone times the derivative of this, which is 9 times 6x to the fifth plus 9 to the eighth times the derivative of that, which is 30x to the fourth. So it's 300 times all of this. Either way is fine. I personally find it just easier to think of the 300 kind of attached to the x to the fourth there. I can definitely do a problem with a fraction. So for those of you in whose class is this I'm looking at? I think Guy's class or Karan's class. These problems I'm doing are similar to web work problem, homework 7, problem number 6. So let's look at this next one. Let's say I've got something like f of x equal to, I want to make it more interesting. Sure, 5x to the fourth over x to the ninth plus 8. Yeah, I want to take the second derivative of that. Well, the first and second derivative. And here, for sure, I'm probably going to want to simplify my my first derivative before I do my second derivative. And the second derivative is going to be gross. So let's find the first derivative. Let's write it here to give ourselves as much room as possible. So the first derivative, I'm just using the quotient rule. It's going to be the bottom, so x to the ninth plus 8, times the derivative of the top, which is 20x to the third, minus the top, which is 5x to the fourth, times the derivative of the bottom, which is 9x to the eighth, all over the denominator squared. And I would simplify. One thing I want to stress here, you cannot cancel an x to the 9 plus 8 and an x to the 9 plus 8. You could if you were able to factor out an x to the 9 plus 8 from this first term and the second term, but there isn't an x to the 9 plus 8 in the second term to factor out. So I really, really, really want to point out that for this problem, you cannot cancel anything right off the bat like that. Although I will also say that for the second derivative, we will be able to cancel some stuff like that, which is kind of interesting. So let's simplify that, because I'm going to have to take the derivative of that, and taking the derivative of the top is going to be really, really gross if I just leave it as is. So it's going to make a lot more sense. Is it going to make a lot more sense? Yeah, it's going to make a lot more sense to simplify this. So let's distribute. So I'm going to have still f prime of x. I'm not taking the second derivative yet. So distributing the 20x cubed to each of those terms. 20x cubed times x to the ninth is 20x to the 12th. 20x cubed times 8 is 160x cubed. And minus 5x to the 4th times 9x to the 8th is minus 45x to the 12th. All of the same thing. And now I would, in this case, also take the additional step, since I have something to the 12th and something else to the 12th, of combining those terms. 20 minus 45 is negative 25. So I'm going to write this as 160x cubed over, minus 25x to the 12th. So I know I've already said this like twice, but I really want to emphasize that when you have to take a second derivative, you want to simplify your first derivative as much as possible to make the next step not so terrible. So second derivative here, taking the derivative of this. So it's the bottom, x to the 9 plus 8 squared times the derivative of the top. So for the derivative of the top, it's going to be the derivative of 160 x cubed is going to be 3 times 160, which is 480 x squared, minus 25 times 12 is 300, right? Because 4 times 25 is 100, and 4 times 3 is 12. So 25 is really, or 25 times 12 is 25 times 4 times 3, which is 100 times 3, which is 300. So it's minus 300 x to the 11th. Minus, now we flip it, right? So doing the bottom times the derivative of the top, it's going to be the top times the derivative of the bottom. So it's going to be 160 x cubed minus 25 x to the 12 times the derivative of the bottom, which is 2 times my stuff to the first power times the derivative of my stuff, which is 9x to the 8th. All over x to the 9 plus 8 squared squared. So x to the 9th plus 8 to the 4th. Now, if I was able to stop here, I probably just would and say, okay, I'm done. Now, typing that in is going to be kind of a giant pain. There is something I should point out when you do a second derivative with a quotient that you can almost always simplify. So when you do the first derivative, you get the bottom squared. When you do the second derivative, you get the bottom to the 4th, but you also get the bottom showing up and the derivative of the bottom, which is when it's something squared, if you take the derivative, you get 2 times your something to the 1st. So what I'm trying to say in a long kind of way is you've got your something and your something showing up, and you can factor one of those out. So the simplification that often happens in a problem like this is we factor out the 9x to the 9 plus 8, and we write this as x to the 9 plus 8 times. Now, I'm not saying you have to do this. You could totally just type in this sort of thing, although this looks terrible. And we factor out x to the 9 plus 8, I'm left with, in this first part, an x to the 9th plus 8 times of 480x squared minus 300x to the 11th. But here, if I factor out x to the 9 plus 8, it's gone. There's only one of them, so I'm left with a minus 160x cubed minus 25x to the 12th times just a 2 times 9x to the 8th, which is an 18x to the 8th. All divided by x to the 9 plus 8 to the 4th. And then I can cancel this one that I factored out with one of those there. So that is some, and then you could do more. Right? You could multiply out the whole top and probably cancel some terms. Yeah, definitely some stuff would cancel. But I don't really want to do that. And we're out of time, so.